be discussing few more other types of questions of capacitance in exams. This is actually a follow-up video of my previous video, numerical related to capacitance. So this is our first question. So say that a capacitor is charged with battery and energy stored is U. After disconnecting battery, another capacitor of same capacity is connected in parallel to the first capacitor. The energy stored in each capacitor. Okay. So it means that you are having a capacitor, and that capacitor you have connected it with a battery, and when you connect it with the battery, it gets charged, and that means certain energy is stored in that capacitor. That energy stored is mentioned here, which is U. And after the capacitor is completely charged, you disconnect it, and after disconnecting it, you connect that capacitor in parallel to another capacitor. Okay, but the other capacitor is also having that same capacitance value. Now, after the connection of these two capacitors in parallel, we have to find that how much energy is stored in each capacitor. Okay, in each capacitor we have to find. So let's say our first case, it's a this question is having two different cases. So in our first case, that let's say that C is the capacitance. Sorry. C is the capacitance of first capacitor, and let's say that V is the potential of the potential. Okay. Okay. So when this capacitor is connected to this battery of voltage V, so as well as that capacitor is also going to have that same potential, that is V, right? And let's say that Q is the amount of charge in capacitor. Okay. So first of all, we are going to find the initial energy, which is given that it is U. So this initial energy U, this is my initial energy when it was connected to battery given there. So it's nothing but half CV square. Okay. Now we are going to disconnect. Once this capacitor acquires this much amount of energy, then we disconnect it from the battery and we connect it to the second capacitor. Now for that capacitor, capacitance value is same. Okay, so this is the capacitance of second capacitor, and when they are connected in parallel, right? So what will happen? A certain amount of charge is going to flow from this capacitor to the second capacitor. Okay, and we are going to assume that initially this capacitor, the second capacitor, is chargeless. Initially, it is chargeless. Alright. Now, once it is connected to this first capacitor, so charge flow from this first to the second, and this flow of charge will continue up to the point where both the potential for these two capacitors will become same. Right. So after connection, after connecting the capacitors, they will acquire a common potential, and that is nothing but total charge by total capacitance. Alright. Our total charge will be Q. Okay. And your total capacitance will be C plus C, and which is nothing but Q by 2C. So this is our common potential. Right. Now we will be finding out final energy. Final energy in each capacitor. So since both the capacitors are having the same capacity, C, it is nothing but half C. Now after connecting these two capacitors, we will acquire common potential, which is nothing but V suffix C square. Right. So this will be the expression for the final energy in each capacitor. So half C. Now this V, C is nothing but Q by 2Z, right? So Q square by 4C square, right? So that Q square by 2C, Q square by 4C square. Okay. And this initial energy, we can again bring it in terms of charge. So it will be nothing but Q square by 2C. This is how we can express. I think in one of the videos I have explained that how this potential energy stored in any capacitor, how we can bring it in terms of CV, how we can bring it in terms of QC, right? And then the third part is how we can bring it in terms of QB. Right? There are various ways in which you can express your energy stored in any capacitor, right? So the QC gets cancelled, and we bring out 4 somewhere here, and if we keep this 2 in bracket. Right. So this is how we have expressed our final energy, and which is nothing but 1 by 4. Remember this part which you see inside this bracket, this is nothing but your initial energy, which is U. That's why we are going to write in place of this bracket part, we are going to write this U. Okay. Therefore, we can say our final energy is nothing but U by 4. Right. So in this question, it is said that the energy, we have to find the expression of energy per unit volume of a capacitor of area A, and the separation between them is D, and their capital potential difference of V. So basically, let's say that this is a parallel plate capacitor, and these are two metal plates, and the area of each metal plate is A. A is the area of each metal plate, area A, and the separation between these two metal plate is D. Okay. So the volume within this metal plates, the volume of the space between this metal plates. So volume of space between the metal plates. So that is nothing but area multiplied by D, the separation between the two plates. Okay. So this is how we express volume of the particular of this space, which is enclosed between these two uh, charged metal plates. Let's say that he is positively charged, and let's say that he is negatively charged. Okay. Now we have to find energy per unit volume. Now this energy per unit volume, energy per unit volume is nothing but your energy density. Okay. In some question you will be asked, find the energy density of any parallel plate capacitor. Remember, it's nothing but your energy per unit volume. Okay. And we have studied till now that when a capacitor is charged by Q amount, so that means we store certain energy in that capacitor. So if I express our energy stored value, so it is nothing but half CV square. So this is the amount of energy stored in any capacitor of capacitance C and potential V. Alright. So since we are doing it for parallel plate capacitor, so we are going to express this capacitance value, which is nothing but absolute not A by D V square. Alright. So this is my total energy stored in any parallel plate capacitor. But since we have to find energy density, so what we have to do, we actually have to divide this energy with the volume of the space between the plates. Okay, so we are going to express this part of absolute naught A by D V square. This is the total energy stored, and the volume. This is my volume. The volume of the space is nothing but A multiplied by D, area into separation between the plates. Okay, so if you simplify this, so this area gets cancelled, and this becomes absolute naught V square by D. There is one D there, so it is going to go. It's going to be in the denominator part. So you will be having a D square term in the denominator. Okay, so this is how you can evaluate the energy density value. Okay, if I represent it by small u. Okay. So this is my energy per unit volume. Okay, so as you can see here, it is option number 8. Okay, so in this question, we have 3 capacitors. Okay, 3 capacitors, each of capacity 4 microfarad, are to be connected in such a way that the effective capacitance is 6 microfarad. So we have to find out that out of these 4 options, which will be the correct connection, right? So we are having 3 capacitors, C1, C2, C3, and all of them is 4 microfarad. Okay, now we have to see which will be the what will be the connection now, in which we can connect these 3 capacitors, so that our net capacitance should be 6 microfarad. So for that, what we will do, first we are going to connect 2 capacitors in series. Okay, so this is 4 microfarad and another is 4 microfarad, and when they are connected in series, so their net or equivalent capacitance will be 2 microfarad. Always remember that when 2 equivalent capacitance or equivalent capacitors are connected in series, the effective capacitance of those 2 identical capacitors, okay, that will be equivalent to half of the individual capacitors. Okay, so since here we are having 4 and here we are having 4, so that equivalent will be 2, and we connect our third capacitor in parallel to this series arrangement. Okay, so their equivalent capacitance is 2, and this is our 4 microfarad capacitor connected in parallel. So our net capacitance will be 2 plus 4, which is nothing but 6 microfarad. Alright, so this is how we arrange 3 capacitors to have an equivalent capacitance of 6 microfarad. It is option number C, connecting 2 in series and 1 in parallel. Okay, so this is our next question. It said that a network of 4 capacitors of capacitance, whose values are given to us. One value is given to us, which is C. C2 value is 2C, C3, C3, C4, 4C. So connected the battery as shown in the figure. So this is the diagram. We have to find the ratio of the charges on the C2 and C4. Okay, so we have to find charge for this C4, this Q4, and we have to find charge for this C2, which is Q2. Separately, we have to find. Alright, as you can see here, this capacitors C1, C2, and C3, they are connected in series, and C4 is connected in parallel to this series arrangement. Okay, so first what we will do, we are going to find the equivalent capacitance of this 3 series capacitors. Okay, now since C1, C2, and C3 are in series. Okay, so we are going to use our series formula, which is nothing but 1 by C net equals to 1 by C1 plus 1 by C2 plus 1 by C3, which is 1 by C plus 1 by 2C plus 1 by 3C. And if you take C common, you are going to get something like this: 1 plus 1 by 2 plus 1 by 3. So our 1 by C net will be 1 by C, LCM is 6. So around it will be 11 by 6. Therefore, C, instead of writing C net, it is C dash. Okay. This is our C dash, equivalent capacitance of this three series capacitors. So this C dash is nothing but 6C by 11. So that means if I want to draw the equivalent circuit diagram, it will be something like this. Okay, so this is my battery V. This is the capacitor C4, and this is my equivalent capacitor C dash. Okay, so we are going to find the charge now. Since the C dash and C4 are in parallel to this battery V, okay, so therefore both of them will have this same potential. Therefore, charge Q dash will be nothing but C dash V. So it is nothing but 6CV by 11. This is the amount of charge in this C dash capacitor. Okay. So remember, this C dash is nothing but series arrangement of this C capacitor C1, C2, C3. And this charge Q dash is nothing but the charge stored in this C dash capacitor. So that means that same charge is actually going to flow through this C3 capacitor, C2 capacitor, and C1 capacitor. Why? Because they are connected in series. So therefore, if I want to know that how much charge do we have in this C2 capacitor, so it would be same as this much Q dash, which is 6CV by 11. Alright. So this is our first charge through C2 capacitor. Now we are going to find charge through C4 capacitor. So it is something but C4 multiplied by V, because it is parallel to this battery. Parallel to this battery V. Now C4 capacitor is having a capacitance of 4C, so we are going to write this 4C multiplied by V. So this is the amount of charge in this fourth capacitor. Now we are asked to find the ratio of these charges in this C2 and C4. So that is why we are going to find the ratio, which is Q2 by Q4. So it's nothing but 6CV by 11 divided by 4CV. So the CV gets cancelled. You get something 6 by 11 into 4. So 6 by 44. So if we do the calculation, so it's nothing but 3 by 20. So Q2 by Q4 is 3 by 22, which is option B. Okay. Okay, so this is another question related to common potential. Okay. So here what it is said that a capacitor of 20 microfarad charged up to 500 volt is connected in parallel with another capacitor of 10 microfarad, which is charged up to 200 volt. Okay, so we are having two capacitors, C1 and C2. C1 is 20 microfarad and C2 is 10 microfarad, and both of them are charged up to potential, let's say V1, which is 500 volt, and V2, which is 200 volt. Okay, and when they are connected in parallel, so obviously there will be certain flow of charges. Okay, and that flow of charges will be up to the point when both the capacitors will be having a common potential, and we are asked to find that common potential value. So what we will do individually, we are going to find that Q1 and Q2 value. So Q1 is nothing but C1 V1. So it is 20 microfarad divided by minus 6 multiplied by potential, which is 500. So we are going to get around 10 into 10 to the power minus 6. So it's around Q1 is 10 to the power minus 2 coulomb. Okay. This is the amount of charge. That means 0.01 coulomb Q1. Similarly, we are going to find our Q2 value. So Q2, which is C2T2. Now C2 is how much? 10 microfarad. So 10 into 10 to the power minus 6 multiplied by potential 200 volt. Okay. So we are having like 10 to the minus 5 multiplied by 200. So it is 2 into 10 to the power minus 3. Okay. So something 0.002 coulomb. This is the amount of charge stored in Q2 capacitor. Okay. So we have to find the common potential. Therefore, common potential, it is nothing but net charge by net capacitance. So our net charge is Q1 plus Q2, and our net capacitance is C1 plus C2. So Q1 plus Q2, we get something 0.012. This is our net charge. Now our net capacitance is like 2 plus 2, 20 plus 10. So it's around 30 microfarad. So 30 into 10 to the power minus 6. Okay. We calculate this, so we'll get something 12 into 10 to the power minus 3. Here we are going to get something 3 into 10 to the power minus 5. 4. So we are going to get like minus 3 plus 5. So it is 4 into 10 to the power 2. Okay. So therefore, our common potential is 400 volt. Option C. Okay. Okay. So this is our next question. Here we see that two condensers, one of capacity C and the other of capacity C by 2. So this is one capacitor C, and this is the another capacitor with capacitance C by 2, connected to a battery of B voltage, shown in the figure. The work done in charging cool both the condenser. Okay, you need to charge both the capacitors. When we say condenser, it is same. Okay, same terminology. It's another term used for capacitor. Okay, so when this capacitors are connected to this battery, so what will happen now? Since the circuit is closed, so both this capacitor will get certain charge, and we are asked to find that how much work this battery has to do in order to completely fully charge the capacitors. Okay, we need to charge both the capacitors full. How much work is required, that we need to find. So for that, what we will do, we are going to find the energy stored in this capacitor. So what we are going to do first, we are going to find the equivalent capacitor of these two capacitors. Since they are connected in parallel, we are going to find our C net. Since they are in parallel, so it will be nothing but C plus C by 2. So this is nothing but 3C by 2. So this is the equivalent capacitance of this connection. So let's say that you are having an equivalent capacitor. This is my C net, and we'll be finding here the energy stored in this capacitor. So energy stored, we express it by U, which is nothing but half CV square. Now in this case, since we are considering this equivalent capacitor, so we are going to write this net here, and since this is connected to a battery of B voltage, so it will be nothing but V square. Okay, so this energy stored is actually going to tell us that how much work this battery has to do to completely charge this both the condensers. So we are going to replace this C net value with nothing but 3C by 2 multiplied by V square. So we are having like 3C by 4 V square. This is our energy stored. So this is the work done. Work done in charging fully both the condensers or capacitors. Okay, so this is option D. Okay, now if you see this question, this is actually very important. Here what it is said that a parallel plate capacitor of capacitance C is connected to a cell of EMF V and then disconnected from it. This is our parallel plate capacitor, and remember we are doing this for vacuum. So this C is nothing but capacitance in vacuum, right? Now this capacitor is connected to this battery of EMF V and then disconnected. So when it was connected to this battery, so he was acquiring certain charge. So that charge is having got Q. Okay. Again, this is charge of capacitor C, which is nothing but CV, right? So the next, what it is asked that it is said that dielectric slab or dielectric constant K. Okay. So once you disconnect this capacitor from this battery, after disconnecting it, you insert a dielectric medium, a dielectric slab of dielectric constant K, which can just fill the air gap in the capacitor, which means that whatever space was there between this plates, the entire space is filled up with this dielectric slab. We have to see that out of this four options, which one is incorrect, which of the following is incorrect. Okay, so we're going to first understand what is this case about, and then we're going to find out that which is the correct answer. Right. So now, when this capacitor, when it was connected to this battery, so he was having this much amount of charge, and when a dielectric slab was inserted, in between this metal plates. So we're going to find all the parameters. Like we're going to find the electric field between the plates. We're going to find the potential between the plates. We're going to find the charge and the capacitance. Every quantity we're going to find here. Okay. Now let's just say that E is the electric field. In vacuum. Okay. When it was connected to this battery, so that E is the electric field in vacuum. Now, when you insert this dielectric slab of dielectric constant K, when a dielectric slab was inserted, then we have this relation that dielectric constant is nothing but electric field in vacuum by electric field in medium. Okay. Now electric field in vacuum is nothing but E, so we are going to replace it by E. Now in this medium, when we insert this dielectric slab, let's say it is E dash. So we are going to find that E dash is a smaller value as compared to this electric field E in vacuum, right? So this expression says that when you insert a dielectric slab between two metal plates or between a parallel plate capacitor, so the electric field decreases by K times, right? Now since electric field is decreasing here, so we should be able to find that what should be the potential difference between the plates. So now this initially this metal plates they were having V as potential difference in vacuum. Okay, V is the potential difference in vacuum. When a dielectric slab was inserted, then it becomes V dash. Right? A V dash is nothing but E dash multiplied by D. Okay, this is the relation. Now this V dash is nothing due to this change in electric field, which is E dash. Initially, he was having in vacuum, he was having this potential V, and which was nothing but E multiplied by D. Right? E was the electric field in vacuum. Now, since that vacuum is changed by this dielectric field, that's why it becomes V dash. So we're going to replace this E dash value, which is nothing but E by K. Okay. So we see that potential difference between the plates after we insert a dielectric slab, that also gets decreased or reduced. Okay. So potential difference gets reduced by K times. Right? Now we are going to find our capacitance value. Now we all know that when a dielectric slab is inserted in any capacitor, capacitance value increases. Okay. Initially he was having this C capacitor, which was nothing but absolute naught A by T, since it is parallel plate capacitor. Now when a dielectric slab is inserted, so this capacitor is going to be something K multiplied by C naught absolute naught A by T, and which is nothing but AC. So it increases by K times. Okay. See, remember, we are doing it for the case when this capacitor was disconnected from the battery. Alright. Now we are going to find the charge value. So initially he was having this small q amount of charge in vacuum. Now let's say that q dash, or instead of capital Q, let's say this small q dash. So small q dash is nothing but C dash multiplied by V dash. Now C dash is nothing but KC multiplied by V dash, which is nothing but 1 by KV. Gets cancelled, so you get nothing but CV, which is Q. Right? So here we have understood that charge remains same. Right? That is conserved. So if we see this option, this option D, the potential difference between the plates decreases by K times. So we have seen that how that potential difference has decreased by K times. This option is correct. If we see option C, the energy on the capacitor is not conserved. But here what we have seen, that energy remains same. Okay, so this option is incorrect. So here it is asked that which of the following is incorrect. So well, this will be the option which is incorrect. Option D is correct. We're going to check the energy stored for this option A and option B. Now energy stored, it is nothing but half CV square. Okay, so we're going to find in dielectric cells. That is why we're going to insert put this dash term. So when we use it for C dash is nothing but KC multiplied by V dash, which is nothing but V square by A square. This K and this K gets cancelled. So you get something half CV square by K. Okay. So U dash is nothing but 1 by K multiplied by half CV square. And this is the energy stored in vacuum. Okay, let's say that it is U by K. here what we have seen, the energy stored in a capacitor when a dielectric slab is connected, but that energy stored also gets reduced by this key times. So here option A is correct. Energy stored in a capacitor decreases by key times. Correct. And the change in energy stored is going to be seen. So initially he will be having this half CV square term. Okay. So this will be the change in energy. Okay. So our correct option is C, because this charge stored in a capacitor remains the same even if you insert a dielectric slab. Okay. Okay. So here in this question, this is a circuit diagram given. So it says that a capacitor of 2 microfarad is charged as shown in the diagram. This is my 2 microfarad capacitor, and you will see a two-way key there connected. This 2 microfarad initially it is connected to this battery of voltage V, and then once this capacitor is fully charged, then it is positioned to switch 2. Okay, this position number 2, it has been positioned. So we have to find that how much, what is the percentage of energy dissipated, that we have to find. Okay. Now when this capacitor 2 microfarad fully charged, so then he will have a charge of, let's say, Q CV. Now in this case, C is 2 microfarad, 2 into 10 to the power minus 6, and V is the voltage of the battery when it is connected to this position 1. Okay. So let's keep it as V. So initially, this 2 microfarad charge, let's say that it is Q1. Okay. So this 2 microfarad capacitor. So this 2 microfarad capacitor is going to have a charge of 2 micro V coulomb. This is the amount of charge stored in this capacitor when it is connected to this battery of voltage V initially. Second case, what is happening here? You are disconnecting this switch and you are connecting this second switch. Now when you connect this switch, what you will see that these two capacitors will be connected in parallel. Right? So it will be, circuit diagram will be something like this. Let's say that this is position 1, this is position 2, and it will be something like this. So this is 2 microfarad and it is connected with this second one, which is 8 microfarad. Now remember, this 8 microfarad initially it was chargeless, so that means Q equals to 0. But when it will be connected to this 2 microfarad, there will be certain flow of charge, and both of them will acquire a common potential. And when this common potential is acquired, so there will be certain loss in energy. So we are going to directly use this change in energy stored in the capacitors. Alright. So this change in energy stored is nothing but U initial minus U final. Okay. Remember, initial energy is nothing but half CV square. So that means it is half 2 microfarad V square. This is my initial energy. And our final energy is nothing but half 2 microfarad plus 8 microfarad multiplied by common potential. Common potential is nothing but net charge by net capacitance. So net capacitance is going to be 2 microfarad plus 8 microfarad. This is my net capacitance, and our net charge will be 2 micro V plus 0, because initially he was not having any charge there. So that's why we are keeping it as 0. Okay, so these are our initial energy and final energy. And when you simplify this two terms, so you will have final expression, which is C1 C2 bracket V1 minus V2 whole square divided by 2 C1 plus C2. Right? So this is the expression of the energy, change in energy stored. Now here C1 is 2 microfarad, C2 is 8 microfarad, V1 is the potential when it was connected to this position 1, so let's say it is V. And since second capacitor was chargeless, so this V2 value will be 0, you will have this only V square. And then again 2 C1 plus C2, so it will be 8 plus 10 microfarad. So this is our change in energy stored. It is going to be something 16. Sorry. 16 into 10 to the power micro and then micro, so it will be minus 12 V square by 2 into 10 into 10 to the power minus 6. So this gets cancelled 8. You will have 8 into 10 to the power minus 12, then minus 1 plus 5, sorry, plus 6 V square. So del U value will be 8 into 10 to the power 5. So it will be minus 7. So it will be minus 7 V square. This is my change in energy stored, or you can say loss in energy when these two capacitors are connected in parallel. But we have to find the percentage change now. So what we are going to do here, we are actually going to find del U by U. Therefore, del U by initial energy. Del U value is 8 into 10 to the power minus 7 V square. Now initial energy, if you calculate this, you will get around 1 micro V square. Micro V square. So 10 to the power minus 6 V square. So this V square gets cancelled. So you will have around 10 to the power minus 1. 8 into 10 to the power minus 1. So this will be your del U by U. But we need percentage change. So what we will do, we are going to carry out percentage there. So 8 into 10 to the power minus 1 multiplied by 100%. So it's around 80%. So this is our percentage of stored energy dissipated. Alright, 80%, which is option C. Okay, so whenever you have to find a change in energy or loss in energy, don't forget this expression. Your loss in energy or change in energy is nothing but C1 C2 bracket open, V1 minus V2 bracket close whole square by 2 C1 plus C2. This is your loss in energy.